Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Izzuddin bin Izlan, and today I will present about my final year project 1, which is manufacturability of water purification system from biowaste. So the content of this presentation are project summary, introduction, literature review, problem statement and objectives, scope and limitations of the project, methodology, and expected result. This project intends to turn selected biowaste, which is eggshells, into an affordable water filtration system. Biowaste will be calcined at certain temperature to eliminate organic compound and to obtain ceramic oxide. Binder also will be added to the obtained ceramic oxide prior to further treatment. And then the physico-mechanical properties of the binder or ceramic oxide will be assessed prior to fabrication of filter model. Moving on to the introduction, the huge amount of eggshell waste produced annually has become an environmental concern because eggshell waste disposal is difficult. Because eggshell biowaste is mostly disposed in landfills, it produces others and encourages microbial development. However, by transforming biowaste into a value-added product like a water filter could have significant of environmental and economic benefits. Next, water is crucial to human life because it makes up roughly about 75% of the body and is required for survival and homeostasis. Every day, humans require between 20 and 50 liters of clean and safe water for drinking, cooking, and basic hygiene. Clean water is also required to prevent disease like waterborne disease, which are easily spread due to the unsafe drinking water system. Lastly, the potential of eggshell as a biological template for catalysis and antibacterial applications. The eggshell could be processed into a powder form and used as a filler with a porcelain mixture to develop a water purification system. Now, let's look at the literature review. Firstly, I would like to talk about the structure of eggshell. An eggshell has 17,000 small pores, bumpy and gritty texture, mostly composed of crystals of calcium carbonate. Calcium carbonate makes up approximately about 95% of the dry eggshell with a mass of 5.5 gram. The average eggshell contains about 0.3% of magnesium and 0.3% of phosphorus, as well as trace amounts of sodium, potassium, zinc, manganese, iron, and copper. The eggshell has 6 layers, which are the uncalcified inner membranes, outer shell membranes, mammillary knob, thin vertical crystal layer, and cuticle. For the next literature review, I would like to discuss about the eggshell as an absorbent. Absorption appears to be the most appropriate method for reducing cadmium concentrations due to enable carbon's high affinity and loading capacity. The absorption of cadmium onto eggshells occurred heterogeneously with absorption energy varying as a function of the surface coverage, since calcium carbonate can be utilized as an absorbent to remove cadmium from contaminated water. Besides, the eggshell waste also could be used as a plant fertilizer to reduce plant blossom and rot disease, reduce the plantation cost, increase plant nourishment, and neutralize acidic soils. Calcium carbonate may reduce the impact on non-renewable limestone sources. The low level of harmful chemicals present in eggshells makes them superior to other natural calcium sources. Due to its high calcium and nitrogen concentrations, some of this waste is used as fertilizer. This slide indicates the literature review of the thermal treatment of eggshells for various applications. The eggshells were placed in an oven for a two-stage thermal treatment. The first stage consisted in heating the eggshells to 450 degrees Celsius for 2 hours at a heating rate of 5 degrees Celsius per minute while maintaining a constant temperature. The second stage comprised in heating the samples to 900 degrees Celsius for 2 hours, but at a slower rate, which is 0.5 degrees Celsius per minute to achieve the desired temperature. At this temperature, the eggshells will turn into calcium oxide by liberating carbon dioxide. The obtained calcium oxide could be used as precursor to produce other calcium phosphate-based materials such as hydroxyapatite. Turning to the problem statement, many research seek to evaluate the use of eggshell waste as other applications. The use of eggshell to produce water filtration system are yet to be explored. The present water filters are expensive and unaffordable to the majority of people. For the objectives of the project are to evaluate the effect of sintering temperatures on the thermal, physical and phase characteristics of eggshell-based composites. Secondly, to assess the effect of sintering temperatures on the mechanical and morphological properties of the composites. And lastly, to quantify the potential of ion leaching using ICP. The scope of this study is to evaluate the effect of sintering temperatures on the thermal, physical, mechanical and morphological properties of the composites. Besides, the possibility of ion leaching will also be quantified. The number of samples for physical and mechanical properties evaluation will be 7. There are several limitations occur throughout the project, which are restriction in the use of the laboratory for samples preparation in Uitm Shah Alam, where a reservation needs to be made due to implementation of standard operating procedure related to COVID-19. Aside from that, the flood tragedy that occurred at the end of the last year caused challenges in the project's ability to progress as planned. This is because the route surrounding Uitm Shah Alam was closed due to the flood. Now, let's look at the methodology of the project. For the material preparation, eggshells will be collected from any nasi lemak stall. After that, the collected eggshells will be cleansed or rinsed with warm water and then dried to reduce the smell of the shells. Porcelain and binder, which is polyvinyl alcohol, will be obtained from local supplier, which is from Maju Scientific Sendirian Berhad. This flowchart indicates the sample preparation for the project. Collected eggshell will be milled with porcelain, distilled water and polyvinyl alcohol for 6 hours. The ratio of the mixture are 42.8% of eggshell, 4.8% of porcelain, 59.4% of distilled water and 1% of binder. And then the obtained slurry form of the mixture will be dried at a room temperature for 48 hours. The dried powder will be sieved to obtain particle size of less than 63 micrometers. The powder will be filled in a mold and pressed using cold isostatic press and sintered at temperature of 1200, 1250, 1300 and 1350 degrees Celsius. For the characterization, the sintered samples will be subjected to evaluation of mechanical and morphological properties using universal testing machine and field emission scanning electron microscope. The crosshead speed during the mechanical testing will be 1 mm per minute. The strength, elastic modulus, and strain of the sample will be recorded. Meanwhile, identification of phase, thermal, and physical characteristics will be conducted using X-ray diffractometer, density balance, and thermogravimetric analysis device. XRD will be used to identify any unknown crystalline phases resulted from variation of sintering temperatures. Physical characteristics such as density and porosity is deemed crucial as it will affect the efficacy of the filtration system. Meanwhile, TGA will be used to observe the effect of sintering temperature on thermal stability of the composites. Finally, the assessment of ion leaching will be performed using inductive coupled plasma machine. Now, let's moving on to the expected results. This preliminary study was conducted using eggshell alone, where the eggshell was calcined at 900 degrees Celsius for 2 hours. The same analysis of the eggshell in Figure A represents the eggshell before calcination process, while Figure B represents the eggshell after calcination process. The graphs show the particle size distribution of eggshell. The graph illustrates the particle size range of eggshell in relation to its frequency. For the calcium carbonate, which is before the calcination process, the highest frequency of the particle size distribution for calcium carbonate is 5, with the particle size range of 55.01 to 60 micrometer. In contrast, the lowest frequency is 1, with the particle size range of 65.01 to 70 micrometer. For the calcium oxide, which is after the calcination process, The highest frequency of the particle size distribution for calcium oxide is 6, with particle sizes ranging from 3.001 to 3.5 micrometer, while the lowest frequency of calcium oxide is 1, with particle sizes ranging from 1.501 to 2 micrometer, 5.001 to 5.5 micrometer, 6.501 to 7 micrometer, and 10.001 to 10.5 micrometer, which are the lowest frequency in its particle size distribution. That's all from me. Thank you.